everybody. I hope you're enjoying CitusCon, an event for Postgres, and I want to thank you for swinging on into my talk. I'm going to be talking about uh, integer to big int conversions. It's an advanced data talk for Postgres. And I've got a bunch of material that we're going to have to cover in a relatively short time. So I do want to just jump right on into it. And hopefully it'll be both educational and a little bit of therapy for those of you who've had to deal with this. And maybe even before you get to that point, this will have some tips that'll help you out. The first thing I want to say is give a warning here. This talk is based on things that have happened in production, sometimes outages, sometimes just on the cusp of outages. So I want to give a warning that the code you're going to see, some of it may work or may not work. I've pulled it together from notes and logs and haven't really tried to make it work because if you're going to use this code, I'll mention in a few places where I think it should just work. Otherwise, you really need to test it for your scenario in order to make sure you don't get yourself into trouble. So we're not going to let you just copy paste it. I do want you to understand what we're doing before you go running this on production in your environment. So with that said, let's get into the problem that we're talking about and see where we are. The quickest way to sum this thing up is a lot of times you'll see this error message, and it's this integer out of range. It's pretty popular. If you Google on it, you'll find examples of this. And the basic problem, and I would say that this technique can be used for other ones, but the basic one we're going to look at today around integers and numbers focuses on this issue that kind of really is in the Postgres community more so than other databases. And it revolves around the three different data types that are traditionally used for doing numbers and storing data like that. There are a few others like floats and numeric and that kind of thing, but primarily when people want to store number type data, they look at these three types. The small int, which is a 2-byte number, goes up to 32,000. They usually decide that's too small. They'll look at a big int number, which is 8 bytes, goes up to about 9 quintillion, give or take. And they kind of decide, well, that's too big and really a much wider range than I'll ever need. And so people settle on the integer, which is 4 bytes. It goes up to 2 billion, which seems like, 2 billion should be more than enough for anybody. So that one is just right. And they pick that one and you're off to the races. And that's usually not a bad choice, at least for getting started and trying to set up your initial schema. In a more practical application of this, the way you see this in the real world, where people will pick a serial data type. And what the serial data type does in Postgres is it takes the integer type, creates a sequence also of integer type, and then maps those behind the scenes to have a dependency and set up a default value. A lot of ORMs and web frameworks and schema management tools like to have a serial primary key where it's just an incrementing number, 1, 2, 3, 4, as you insert rows into that table. And that's fine. Like it is what it is, or at least I'll go say that for the moment. I will let you know there is a big serial version of this, so you may see that out in the wild, but it seems to be much less commonly known. And the default, again, in most schema creation tools, defaults to this serial type, which uses integers under the hood. I don't want to really get into a big debate on logical versus surrogate keys in this talk. That's for another day. We're also not going to discuss the merits of UUID-based primary key. It is a thing maybe to think about, but we will talk about it at the virtual bar, I guess, maybe later. I'm happy to have that discussion. But here we're just going to sort of focus on the problem at hand, which is serial data types, integer data types, and how we get into and out of trouble with those. One thing I want you to keep in mind, if you run into this in the wild or when you hear stories about this kind of a problem, the first thing to keep in mind is this is usually a surprising issue. Like you'll see that error message suddenly and nobody really realized that this was a thing that was going to be a problem. And because of that, you can imagine these types of problems often have to get fixed under duress. Meaning, you have an order table when suddenly you hit your, 2.1 billion-ish order, and now you can't insert any more rows into that. So you can't take any more orders, and everybody gets on the phone and starts going a little bit crazy. So the other problem that you can see is you can pick a data type that you think is going to work, and it might take you a few years before you even hit this issue. If you were doing 100 million inserts, a month, let's say, it would still take you, over a year and going on close to 2 years before you would actually hit this problem. And the people who pick those data types may be long gone from your organization. So institutional knowledge about this could be rare and hard to find. And finally, sort of the last real issue that pops up is that you can be dealing with a fair amount of data in this case. Like let's say 2 billion rows is not uncommon when you have an integer overflow. That kind of data can certainly make everything harder. You can't just do a rewrite of the table real easily, especially if you need to be able to keep doing inserts and updates on it. So if it's such a problem, you would say, well, maybe we should spend time trying to avoid the problem, right? Let's just not ever get into it. And are there any tricks, or how do I do that? And there are techniques you can try, and we'll see, how well those work or not. The first one that usually people say is like, well, let's just use big ints everywhere that we need them. Meaning if we know we're going to go over 2 billion, pick a larger data type, and that should do the trick. But again, like I said, these are usually surprising cases where you run into these error messages with the integer type. So it's really hard to know a priori where you actually should be using big ints versus regular integers. The other thing you can run into are bugs in like ORM or schema tools. I don't know if it's a famous one necessarily, but one we've seen over and over again is in Django. A few years back, there was one where you would define tables using the big serial data type, and it would create your sequence in a way that it would use a big int data type, but it would still create the table, and the column in the table, the ID column, would still be created with an integer type. So this was, sort of doubly bad and extra surprising, because if you ever looked at your sequences, you thought, oh, these are all set up really nice and perfect. And you really had to look at the table to realize like, oh no, this is not going to work. This is going to break. So watch out for those kinds of things. Bugs happen. The other thing that can be a problem is artificial escalation. Assume that like, okay, well, we probably won't ever get to 2 billion with normal insert activity. But then for some reason, somebody says, well, we're going into a different market. Like if you're starting in the US, we go into the European market, and all the European orders, we'd like to start those, like plus 1 billion from where the current number is. And eventually there's talk of sharding and all that. If you suddenly start jumping your numbers up in a way that doesn't correspond with inserts, obviously you can get to 2 billion a lot faster than you might have thought. So be aware of that. That can definitely be an issue. The other thing that people will do is they take sort of a stronger approach and say, well, what if we just use big int everywhere? And you can do that. Just be aware, and this is usually what sort of knocks people off of this path, is that you are going to probably have to use more space on disk, whether it's in the table or in the index. It'll take more RAM, more swap potentially for queries, more network usage as you're sending data back and forth. And that usually, like people say, well, I don't, I hate to waste the resources, quote unquote, waste the resources on numbers that aren't actually that big. And I think that's a valid take to have, although I will mention there are other databases, Cockroach as one example, where whether you specify an integer or a big int data type, it actually maps to an 8-byte number under the hood. So either way, you wouldn't run into this problem on a Cockroach system. So be aware that is how some other people will handle it, and that's how other databases handle it. That's an option. Of course, somebody in the crowd wants to say, hey, we could just use UUID-based primary keys and this will all go away. But as I mentioned, we're not going to talk about that in this talk. So let's just put that out of our minds for the moment. All right, so if we can't be sure that we will never run into this problem based on schema design, I think the other thing people would say is like, well, how do I get a heads up on the problem so that if it is going to happen, I know in advance, I have time to deal with it? And I think there are some things you can do. It's not quite as simple as it looks in the beginning, but I've got some code here to help you out. The first thing I think about is like, this is, I think, most people's initial check is I'll just select a max ID number, right, for my primary key from my table. And if I do that query, on the regular, that should really be fine. It's a primary key, it's indexed, it'll be a very fast query. Even if you have, 500 tables or something, 500 of those lookups are not going to be that big of a stress on the system. You also don't really need to do this, every 5 seconds or something. Like you could run this report probably once a day. Certainly you don't really need it more than once an hour. And it should give you a pretty good heads up on any problems that you're going to run into. Just put some thresholds in place low enough to get you the heads up. So this is probably fine, but the problem is that it doesn't cover everything. You have to start thinking about, well, what if I have foreign keys now that are referencing these IDs, right? It's part of why we have the primary keys to set up foreign keys. And so that would be, another query. Well, select max of a parent ID from the child table. We'll reference that back. If you want to do this, you probably have to build some extra indexes. By default, Postgres does not create indexes on foreign key columns in a child table. And generally that's because on insert, you really only need to look up in the parent table, not in the child table. So we don't build the indexes from a Postgres standpoint to save you a little bit of overhead. If you're going to run queries like this, you're definitely going to need to put those indexes in place. So that may be a good reason not to do this, or maybe a problem if you want to try to do it. There's other cases and other issues around this. One of the ones that I've found is certainly when you start talking about billion row systems, and that's the world that we're living in with this kind of a problem. I've often seen people will drop their foreign keys in order to work around like locking and performance issues. And that could have happened again years ago because, again, these problems can take years to develop. If you're doing that, it may be hard to figure out where all the parent and child relationships are. It won't also account for things like externally referenced IDs or sharded IDs. If you've got a user in an order table and now it's a user database in an order database, those orders still need to reference a user ID, but there's no easy way to look that value up, right? Because now it spans into another database. So you'd have to go kind of through every column and figure out where those numbers actually relate to. And this isn't even talking about integers that might not be part of any kind of a foreign key anyways, right? If it's coming from another API or something along those lines, you're going to get a number back. You have no idea what the rate of that will necessarily be. And I haven't even started talking about integer arrays, which is another sort of case you need to be able to handle. So it's not quite as easy as just doing some simple lookups, but I have put together a query that looks a bit scary, but don't worry, I'll walk you through it real quick. This one you probably can copy and paste right into your system and you'll get a report back if you want to do it. And I know it's not the easiest thing to read off of a slide. I can get you copies of that or copies off the slide later on. But it's not as complicated as it looks. The first step, and this will make sense as we walk through it, is we basically say to the database, let me look through the system catalogs and I'm going to pull back every integer column that is in my database for every table, right? I need to basically look at everything that's in there in order to verify and make sure that I'm doing okay. Once I have that list, I can go look in the statistics table that Postgres gathers to understand the shape of your data for query planning. And I can use that information to get an upper and a lower bound of where Postgres thinks the data lives in your table, and then use that to build a report to give me the table, the at name, which is your column name, and then the min and the max values from those. This query will be pretty fast on a 500 table database. This should come back in like a second or two at the most. So this is a pretty cheap query to run. And this will get you a pretty good idea of both you can run it multiple times and get a rate of change over a few days, or figure out where you are in that. I do have to say, though, even this is not perfect. Like, I think it's a really good way to find out this information. But, for starters, it's only good as your last analyze. So if you have tables that aren't getting analyzed regularly, if you're on an older version of Postgres where it's an insert-only workload, that's one kind of example that could definitely fall prey to an overflow, but also not be getting analyzed regularly. So watch out for that. You have to watch out for negatives, and we'll come back to that a little bit later. But watch out for negative values that might be in there, which can throw some things off. And again, this probably isn't going to protect you from artificial escalation. Hopefully you'll catch it soon enough. But if somebody says, let's jump it by, 2 billion or something, you're going to be in overflow land in a hurry. So just keep that in mind as you're going through it. So if we can get the heads up, or maybe we can't get the heads up, right? The real question is, what do we do if we see this error message in production, right? That's our production emoji, of course. So let's say you see it and somebody calls you and says, hey, we got to do something about this. All right. Well, what is the fastest, cheapest, quickest thing that might get you out of trouble? That is actually this piece of SQL. And it's pretty straightforward. We're just going to alter the sequence, right? If you remember, these columns typically have a default value, which is calling the next value from a sequence. So if we alter that sequence and we change the minimum value to be a negative, and then we restart it at that negative value, right? And we're going to the negative range for integer values in Postgres at negative 2.1 billion-ish. That will actually buy you some time to work on this problem. By default, sequences start at 0 and they go up to positive 2.1 billion in Postgres. So this gets you 2 billion roughly transactions, to actually fix the system and address it. And I say, like, this is super cheap, right? This is a quick metadata update, and then you're back in business. Hopefully, be careful if you're doing, I would say kind of odd things, like if you rely on the order of the primary key value to actually be in like a time order. So you judge like, well, this is a later one than that one because the number is larger. In code, like humans can probably figure this out, but in code, you've got to go back and adjust for that because now your negative numbers are going to be the new ones, right? And it will just start climbing up towards zero. So keep an eye on that. This could also cause some issues for your apps, but again, we'll cover that in a few minutes. But I want to get you again. This is sort of like the cheapest, easiest, like pulling the emergency brake fix in order to solve this kind of a problem. If you have some time, or even if you don't, and you need to be able to sort of try to rebuild some things on the fly, this is a version of a way to solve this problem and actually keep things moving. I'm going to imagine we have a table called M. It has a column Y, which is a serial, so just an incrementing number going up, and then another column Z, which is a JSON-B column. And you store all your data in the JSON-B, and you have a primary key there. Maybe you ported it from Mongo or something. I don't know why you would design it, but let's just say, for example purposes, table M is there. You hit the integer. What you can do is, first you start by altering table M. You're going to add a new column called future Y, which will be a big int column. And then you're going to use that column in order to track new data coming in. And Postgres, one of the nice things, of course, is it has transactional DDL. So you can make these kinds of changes, basically transparent to your application. You need a lock to be able to get the change to happen. But outside of that, once you get that, you can make a bunch of changes under the hood. Here, you would take the table and rename it, let's say, to something like other M. You create a view called M, which will then coalesce the original Y and the future Y column. So whichever one of those has a value in it, we take that value, we return it as Y, and then we also return Z. From a client perspective, that view will look just like our old table. And then, of course, we are going to need some triggers in there to handle inserts, updates, and deletes. They're now going to go to the view. Depending on what you're doing and the types of things your application is doing, that may just work, but you may need triggers in order to handle it. You probably will need triggers in order to handle it. Mostly for being able to set the future Y values to the incoming Y. So if a client tries to pass you a number for Y or is looking something up by Y, you need to handle a little bit of juggling so that future Y actually gets that value, which will become a big int value. Once you have that going and you have that system in place, right, you've got your triggers, you got your view, you got your table, that's going on and handling your inserts and updates, as needed. You then have to backfill the existing data. So you've got, the first 2 billion rows in the table all have a value in Y. Anything after that has a value in future Y. So you've got to go and update all those rows so that future Y also has the Y value, right? So it's just a bunch of updates. Don't do it all in one go. Batch that thing up as you're doing it, and then move on from there. And then once you get that all backfilled, right, then you're basically going to do this transactional DDL in reverse. So you take the view, you rename that to something else like old M. Now take your table that you had renamed previously. You can drop column Y or just rename it, but get it out of the way. And then you rename future Y to Y. And then alter that table other M, rename it back to the original name M. And again, your applications won't really notice this change in the middle here. From them, there'll be a brief sort of lock that goes on, and then M looks like M every time. Now, of course, this does get more complicated if you've got, primary keys and foreign keys and, other dependencies that are involved. But all of that stuff can be worked out. I've done some really complicated versions of this where, there's pages of SQL between this begin and commit. And in Postgres, most all of that is metadata changes. So it is really fast if you have to do it. And that gets you back in business. So keep this kind of idea in mind, where you can do these alters and alter tables and whatnot and move them forward and keep things moving forward. You can actually also play the same trick if you want to put a view on top of two different tables. So in that example, we just added a new column. That's kind of usually the cheapest, easiest thing to do. But you can actually make a whole separate table and then put a view and join the two tables underneath the view. And again, from the client's perspective, all they see is the view that looks like the table. You can actually even do this with logical replication or foreign data wrappers. It's just more complex because now you're sending the data off to another system. But again, I've done that one. It can be done. Under duress, it's probably not the thing you're going to do. You're probably going to do something like just add the column. But if you have time, if you catch the warning, 500 million entries ahead of time, maybe you want to look into doing something like that. Of course, fixing at the database level is only one side of the problem. There are other things we really have to consider. First off, if your app was based on an ORM or some kind of schema tool and it defines these columns as ints, you need to go back and update that. Tell them it's now going to be a big int and see what changes that will make for the application. The other one, and this is not a fun problem to hit, we've done it where we've done the int big int conversion, started plugging in values and thought we were on our merry way. But some programming languages, like I said, in Postgres, integer means negative 2.1 billion to positive 2.1 billion-ish. And some languages, they use an unsigned int, which takes you from 0 to 4.29 billion. So you'll start putting in those, 2.1, 2.2, 2.3 billion entries into your table just fine. And then, another couple of years down the line, this will break on the application side as it tries to put in a value that is okay from the database's point of view, but the app doesn't actually know how to handle that. Also, as always, remember modern systems are much like ogres. They have layers. So you have to think about where are these values coming from? Where are they going to? If you're backstopping an API and you haven't, you haven't made a change, or you got to sort of announce that there's going to be a change, people might expect that your numbers are going to be integers because that's what your API says, and now you're suddenly sending different ones in. Another really fun version of this problem is if you have compiled code. Let's imagine you have a table that is the backing store for a web app, for a mobile app that you have sent out to people. So you now have to recompile the mobile app to understand I need to be able to handle big int numbers, maybe upload that to some kind of app store, hope that people will go and download it. Try getting Apple to do that in a hurry, on a Saturday night. I'm just saying, if you can get the early warning, you definitely want to get the early warning, because otherwise these kind of problems, they can be lurking out there. So be aware of that. The other thing I did want to touch on before we wrap it up, let's say you're in one of those cases where you say, well, I know I can make the database change, it'll be good. How do I actually figure out whether all my apps can handle this? And one of the things is I mentioned, both you have sort of like the unsigned int where they might handle the data type oddly. The other problem with that is with the unsigned int, it's from 0 to the 4 billion range. And thinking about that means if you do that emergency break where you set the value to negative, your app may not actually know how to handle that, right? It may error out on the application side because you've sent it a negative value. So if you want to do some testing, this is a function we've used. And again, keep in mind that usually the default on a table, if you set it up as a serial, there's a next val, which is just a function call like any other function. Calls into a primary key sequence that's been set up. You can make a separate sequence for that. And in this code, what we're basically doing is saying we're going to take a random number based on some percentage. We'll either call our normal sequence, or we have an experimental primary key sequence that we will return instead. And you can use that to change the value all over the place with the sequence, set it up to 2.3 billion, set it up to 5 billion, set it back down to a negative, and send some small percentage, 1%, 10%, whatever you feel comfortable with, to send entries through your system and let it go end to end. And that way you can test the application side as well as the database side. All you have to do when you're done with the experiment, you can just turn it off in code here, because any change is now just a function recompile. You don't actually need an alter table once you have this in place, or you can do the alter table and set your default back to just the sequence number once you're good to go. But this is a kind of trick that, again, Postgres gives you some nice tools to be able to handle this. And so you can build your own function with whatever logic. Maybe do it instead of doing a random, maybe do it based on like, oh, is this a user? Like, is this user account somebody who's internal to the company versus external? Whatever logic you want to be able to put in there, you can make a function like this, make it your default, and then start doing those experiments. So hopefully all that, I know, is a lot of ground to cover in a short amount of time. I hope that helps you out before you run into a production problem. If it has to help you out during a production problem, well, I guess that's equally good on some level. So that's all I have for today. I want to thank everyone for tuning in. Thank the folks at Microsoft for having CitusCon. And if you have any questions, feel free to hit me up. I am at RobTree2 on Twitter, and happy to go through any more of this in details if you want. So thanks again, everybody. Hope to see you online.